So I'm David Mobley. I am very involved with open force field and to a lesser extent with open free energy. I'm going to be doing a tag team with Lily Wang, open force field science lead. So I'll do kind of an intro and then she'll take over and then I'll come back up at the end. In case you made it to this meeting and you don't know what a force field is, which probably is not most of you, but just in case, a force field gives a energy of a system consisting of atoms and molecules as a function of the positions. It's not a magical Star Wars thing, use the force. Although, if you're talking about force fields on an airplane next to, people who don't know, it can be a little bit entertaining. So we're about building force fields, accurate descriptions of energies in atoms and molecules in order to help guide biomolecular design. Just at the beginning, this is kind of my assumption going into this talk, but I realize not everybody knows. Open force field already builds the best public small molecule force field. This is just one way of looking at accuracy. Higher curves are better. And so you can see as we've gone across different open force fields versions, the force fields have gotten better, and GAF is generally the best public other option out there. So I'm not going to be talking about that because it's background, but you can ask us about that later. So as you already heard, this has been a year of growth. We brought on some new people, partly funded by the NIH grant. But also on the right-hand side, this is kind of cool. This is growth in how many CPU hours we used on one specific facility over the course of the year. And so we use that to run something like 75 different full force field fits, which is really cool. And, especially because a force field fit used to take almost like years or decades for people. It's also cool because it shows that our plan that we've stumbled across is working. We used to come in with an idea and spend a huge amount of effort developing that idea and then find out it was a bad idea. So we've switched more to a model where we have a bunch of ideas in a hopper and we shove them into the pipeline and we see which ones actually end up being good. So if we did 75 force field fits, it means that we're succeeding at testing our ideas rather than investing a whole bunch of effort in each one individually. So our impact, along with that, we think is continuing to grow as the project matures. We've been around a while. To some extent, the project started when Chris Bailey arrived in sabbatical in my group in 2016, but we didn't have funding for a while. Happened that my daughter was born on the day he arrived, so I can basically track the growth of the project with my daughter. So it launched with funding in 2018. Then, so there's my daughter there. 2023, we had our first meeting, so that's last year, starting to look a little more grown up. And now we are off to the races, commercial vendors and so on. So OpenEye, for example, relies a lot on our force fields. And so we're really excited about that and excited about the things that are coming. We're also now, you're getting to hear about what we're doing with the large amount of data we're generating. On the top left is a graph of records, quantum chemical records being deposited in QC archive. Huge growth at a couple key points. There's some news here from Mobley. On a particular day, we were generating 12 different quantum chemistry results per second into their QC archive, which was a new milestone. And on the bottom right, you see different supercomputing facilities being used all over the country for that. And on the left, a graph of CPU usage. So you hear about what we're doing with that data. Also, and you'll hear more about this from David Dotson, I think, but we're really excited that now we can run free energy calculations at scale to test our force fields, partly in collaboration with Open Free Energy and others. And so this is a graph looking at the number of free energy calculations that have been run with infrastructure we help build now. So some other cool things you're going to hear about. One is that we've had big problems with, we've observed big problems with choice of partial charges impacting, or how a user provides a conformer impacting the charges which impact binding free energies by up to about 5 kcals per mole. And so you're going to hear about how we can fix that with graph network charges and what other great things that's going to do for you. We've also run a series of really nice workshops that we've already gotten quite a bit of positive feedback from people about these, showing people how to use our tools to do different things. And attendance of these is way up from before. So we're excited to see the tools getting out there. And we're also excited about the fact that our infrastructure is enabling other people to do cool things. We don't think we have a monopoly on making good force fields. We want to make it so people use our stuff to make great force fields, whether we do it internally or not. And so a great example of that, those of you at the alchemistry meeting heard about this from Ken Takaba with John Cadera and others, building an Espeloma machine learning force field that's really exciting in a number of ways, and we're able to help them use our data sets for that. So I'm going to hand over to Lily now to give you a little bit more update on what's going on. I'll come back up.
Cool, thank you, David. So as David mentioned, there's been a lot of progress since the project was first started in 2016, and along both science and infrastructure. So just to kind of set the stage, I want to go over some of the major milestones in this very long timeline before I start describing and summarizing what we've been working on in the past year. So in 2017, that's when the OpenFF toolkit first launched, and that's what enabled us to first release our first force field, Smirnov 99 Frost. And this, for the first time, was a force field encoded using the Smirnov format that allows us to assign force field parameters to molecules using direct chemical perception instead of needing to define formal atom types. Next, in 2019, integration with both force balance and the QC archive enabled us to start refitting bond, angle, and proper torsion parameters to a growing corpus of quantum chemistry data, as David showed, and enabled the next generation of force field releases with valence parameters refit. In 2021, we released our first force field with non-bonded parameters refit. So specifically, we fit van der Waals parameters to condensed phase properties. And this was another milestone achieved through the use of amazing infrastructure, so specifically the OpenFF evaluator launched 2 years prior. And then last year, we released Sage 2.1, the first force field in which we refit improper torsion parameters. So that brings us to the past year. And for the rest of this talk, I'll spend most of that on firstly describing Sage 2.2, the force field that we just released this year, as well as giving an update on some other projects that are still in progress. So last year on our roadmap, we committed to 2 goals. The first being to continuously improve valence parameters, and the second being to create a generalized benchmarking suite, now named YAMS. And over the past year, that's exactly what we did. So you can think of this slide as kind of a zooming in of the broader timeline on the previous slide. And the idea here is to show that, as David mentioned, there's a lot that goes on behind the scenes before we actually publish a force field. You don't have to worry about reading all the text, but the basic color key here is that all the dark blue projects are things that did make it or will make it into a public force field. And all the gray projects are research directions that either didn't pan out or were projects that related more to technical and workflow needs. So, as I said, in the past year, we released Sage 2.2, and this force field updated valence parameters with a specific focus on improving small ring angles and sulfamides. So to demonstrate exactly what impact that would have, you can see here 2 examples of somewhat distorted geometries in Sage 2.1 that are now mostly fixed using the updated parameters in Sage 2.2. And maybe for a more data-driven look at that, here are some parameters that were affected by the force field refit. So these specific angles are sulfur angles that would have been applied to the sulfamide geometry. On the x-axis, we have the difference between the angles from our MM force field compared to the QM. So basically what we're looking for is as narrow a distribution as close to 0 as possible. And you can see this pretty nice improvement across Sage 2.0, 2.1, 2.2 of firstly moving closer to 0 and also getting rid of some nasty outliers in the geometries. So we're going to continue improving valence parameters, and as part of that, I just wanted to highlight one project that didn't quite make it into Sage 2.2, but it's really promising and will feature in the next force field release. So here, this is the idea here is that we have a lot of torsion parameters in our force fields that cover torsions with multiple multiplicities. So a torsion applies across a central bond, and based on the number of substituents across the central bond, a different number of torsions will apply. And the idea here is if we separate out these joined connectivities, we'll be able to target specific chemistries in a much more targeted way and treat them more accurately. And indeed, this is still an ongoing project, but our preliminary results are showing that our structures really improve once we do this, as shown by the improvement on our geometric benchmarks. So this is a cumulative distribution plot, and again, we want the curve to be higher as we get closer to 0. So that's the force field that we just released. I'm going to now start talking about some of the projects that we have in progress, starting off with the protein force field. So this was quite a high priority on our roadmap for the past year. And this is a project that's being driven by Chapin Cavender, who hopefully is in the audience here today. Yes, that's Chapin, thank you. And he's based at the Gilson Lab in UCSD. So over the past year, Chapin has put in a lot of work into investigating a lot of different approaches to bringing out a full-blown protein force field. So I'll start off by first recapping the goals of this project for those of you who aren't familiar, and then give a status update on where it's currently at. So up until now, all our force fields have really targeted the small molecule area. And this expansion to proteins is our first foray into the wider area of other chemistries. So just really our first initial goal is to have parameters that cover both small molecules and proteins. We want to co-optimize these parameters to training data so that they're self-consistent. And we want to achieve similar accuracy to already existing protein force fields, such as AMPA14SB. At least initially, we want to remain maximally similar to our existing small molecule parameters. And as part of this investigative effort, we want to see if we need to add specific protein torsions to achieve good performance, or if our small molecule torsions that already exist can generalize. And Chapin has been investigating along both these directions, so he's fit force fields both with these torsions added and labeled them specific, as well as force fields without these torsions that are called null for the null hypothesis. So moving on to where this project currently is at, the main focus of the project right now is trying to improve how our Smirnov force field candidates treat secondary structure. So one of the key benchmarks that Chapin uses to evaluate our force field candidates is simulating a folded protein in long timescale simulations in water. So in this case, the GB3 protein shown here. Using the already existing AMPA14SB force field as a reference, we see AMPA14SB does a great job here. It's very stable in solution, and it's stable across all 3 replicates. With our force fields, though, what we typically see is that some of the secondary structure unravels. So in this case, with TIP3P water, in at least one replicate of both the null and specific models of one of our previous generation of force fields, we see the alpha helix, or a portion of it, unravel here. And I've only shown the previous generation here, but this is a pattern that we see across a number of our force field candidates. So this is impacted by the water model that we use. We see that if we switch to a different water model like OPC, so AMPA14SB, again, remains relatively stable in solution, and the alpha helix actually also remains stable in our force field candidates, but on the other side of the protein, the beta hairpin starts unraveling instead. And we can basically summarize the results that I showed in the previous 2 slides on this graph over here. So this is a graph comparing scalar couplings across each of the 3 force fields I just mentioned and across multiple water models. And lower is better on this graph. So AMPA14SB, it's pretty robust to different water models. It remains folded, GB3 remains folded in solution across each of these. But for each of our force fields, the 0.0.2 versions, we see some destabilization of secondary structure. Another benchmark that Chapin uses to evaluate force fields is one where he takes a peptide chain 15 residues long, and he simulates it to see if it folds into a helical coil in simulation. So this is another thing that AMPA14SB does quite well on. The blue diamonds here represent the experimental measure of helical fraction across the peptide. And all the other colored diamonds here represent different ways of computing the helical fraction from simulation data. So at least for the orange and the pink diamonds, we see that with 14 sp in tip 3p water, the curve is pretty much spot on. With our force fields, however, what we see is essentially no helical fraction at all. The peptide is not folding. And again, I've only showed one force field candidate here, one of our newer fits, 0.3, but this is a pattern that we see across pretty much every other force field candidate that we've looked at. So that's a problem that we're still trying to work through. That being said, we have made a couple of exciting breakthroughs over the past year. So, for the first time ever, we have a force field candidate that maintains GB3 structure in solution. Yay! That's this one here, there's a pink arrow, and that's null 0.3 in OPC water. The problem is, however, you might notice that's the exact same candidate I showed in this benchmark with this water model, so this still doesn't fall into a helical structure in simulation. On this benchmark, though, we had a different force field candidate, also from the most recent generation of fits, show a lot more promise here. So in tip 3p water, the specific version of this force field does fall into a helix, and that's also really amazing. Of course, the problem is once we take it back to the GB3 benchmark, that's this column here, we see that the secondary structure is still destabilized in solution. So this project is still very much ongoing. It's definitely a high priority on our roadmap for the oncoming year. But we're optimistic, and we look forward to the day when we have a full-fledged protein force field, and we can create a protein ligand simulation and export it to our favorite MD engine in less than 10 lines of code. So moving on to a slightly related project, we've been working on a neural network model for assigning partial charges. And this, again, is a multi-year project that we've made progress on this year. So this year, we've actually managed to publish 2 release candidates that we're pretty happy with. Again, just to recap the goals of this project. So the canonical charge model that we use with our small molecule force fields is AM1BCC. And that is a charge model based on quantum chemistry methods. So much like many other quantum chemistry methods, it has 2 main disadvantages. The charges that you get out from the method are heavily dependent on the conformal geometry that you put in. And also, it just doesn't really scale well to larger molecules. So the aim of this project was to have a charge method that would assign AM1BCC-like charges to small and large molecules efficiently and without conformal dependence. And this project is codenamed NAGL. Just to really hammer home why we care so much about conformal dependence, the OpenFF toolkit uses 2 different backends to assign AM1BCC charges. So we have OpenEye on the left-hand side here, as well as our open source, free and open source alternatives, AmberTools here. And one thing that AmberTools can do, if we continuously give it different conformers, is assign wildly random charges to the same molecule, but with different geometries. And if we do that repeatedly across a protein ligand binding free energy project, as was done here, we can get really weird results. So we can see there are some massive error bars here. If we take care to not do that, to only use one conformer to assign charges, the results start looking a lot more normal, and actually the performance of OpenEye, AmberTools in the third column, and NAGL, the neural network model, is very similar across this benchmark. So what OpenEye does on the left-hand side here is it uses the ELF10 variant of AM1BCC to mitigate this. And what that does is it averages the charges of up to 10 structurally diverse conformers, and that kind of gets rid of some of the charge variation. But the really big advantage of NAGL is it totally avoids this issue. There's no conformer dependence whatsoever. So moving on to the benchmarks and how it performs. The 2 benchmarks that I'm going to show here today, they both use OpenEye ELF10 as the reference, because that's the charge model we're currently using to fit our force fields. And I'm comparing the NAGL release candidates alongside AmberTools as kind of a measure of acceptable charge variance. And the basic gist of the slide is that on small molecules and peptide chains, the variance of NAGL is well within the variance of AmberTools. So we're quite happy with this result. And it's pretty much the same story with this benchmark as well. So this is solvation free energies of small molecules in aqueous and non-aqueous solvents. The performance of both Amatools and Naggle is very, very similar to OpenEye. And of course, one of the main reasons we wanted to do this was speed. So comparing the neural network model to any other method, the neural network model blows everything out of the water, including library charges that uses pattern matching to assign charges. So the release candidates of Naggle are publicly available for use. If you're at all interested in these models, we would really love for you to try them, and we would welcome any feedback and any issues you run into so that we can improve the model. The easiest way to do this is probably through the OpenFF toolkit using the Naggle toolkit wrapper, although with the caveat that there are some safeguards built in here. So if you try to assign charges to a molecule with a bond type that is outside the training set, it would just refuse to assign charges and it will raise an error. If you really want to get around this, you can by using the model directly, but obviously we can't really say much about the quality of charges you get out. And I believe in tomorrow's demo, Jeff will give an example of this. So I just wanted to take a moment and highlight that we're quite excited about Naggle and about all the capabilities that this can open up, especially in tandem with the protein force field. Right now, modeling post-translational modifications and non-canonical amino acids, that kind of system, is a fair amount of work. This time last year, Jeff showed a demo where he tried to assign parameters and successfully assigned parameters to this modified peptide chain. It's a very long notebook, so I've just really snipped out the part here where he assigns charges to this. And it's a bit of a process. So what you have to first do is you have to snip the small molecule part off because the normal peptide chain gets normal peptide charges. You need to add a cap onto the small molecule part, assign M1 BCC charges, take the cap off, account for the fact that the molecule still needs to have an integer charge, and then splice the whole thing back in. So as you can see, it's a fair amount of code, and it works. In fact, this is a popular enough thing that people want to do that Jeff actually worked with Rebecca Alford at Janssen to get this to work in simulations of modified cyclic peptides. But it's just kind of a hassle. With Naggle, and especially in concert with the protein force field, what we should be able to do is assign parameters and go straight to simulation, exactly the same as any other molecule that the OpenFF toolkit can currently handle. So it should basically be as easy as just putting it in the toolkit and assigning parameters. So that's the future that we're all working towards. Moving on, the next thing I'd like to talk about is virtual sites. So again, as part of our roadmap, this is a new project that we started working on this year. And the motivation behind this is that there are some features of the electrostatic surface that are just quite difficult to model with our force fields as they currently are. So atom-centered fixed charge force fields. If we add a virtual particle, we can add a lot more complexity. And what we can actually do here is we can reproduce this sigma hole feature around the bromine if we add a virtual site. So the initial phase of our virtual site plan is not very ambitious. It's mostly targeting low-hanging fruit, the sigma holes of chlorine and bromine, and the lone pair of pyridine. And this is a project that's still very much in progress, so we won't get too much into detail here. But basically, we're getting reasonably promising results. So on condensed phase properties, if we go left to right here, we see that if we retrain our van der Waals parameters and our bond charge corrections relative to vanilla stage 2.0, we get some improvement. We get a lot of improvement if we add an additional nitrogen van der Waals parameter. And in fact, we actually can correct a systematic error with amines and water for enthalpies of mixing. And then at least on this overall data set, adding virtual sites maybe slightly improves things. It doesn't really change things overall. Although noting that we expect virtual sites to matter most in directional applications. If we take a subset of the data, so if we actually look at the molecules that we add virtual sites to, the trend is a bit more clear and the improvement is a bit more clear. So at least for pyridine and for chlorine, the results are promising. But a major reason that this is still very much in progress is that we're running into issues with bromine. So pretty much as soon as we start retraining the non-bonded parameters, the condensed phase properties take a hit in performance. And it's not just us doing cool things. As David mentioned, one of the great things about OpenFF infrastructure is that it really enables a lot of other people to work with it. So Josh and Danny, who are also both in the audience today, they have been working on an alternate functional form using the double exponential to model non-bonded parameters. So what they've been doing here is they've been co-training their non-bonded parameters with both QM dimer data, as well as on physical properties using Simon's Me software. And the results are looking pretty promising. There's some reduction in error on both condensed phase properties and quantum chemistry errors relative to the conventional Leonard-Jones form. Right, so that's some of the highlights of what's been going on in the past year. I just really quickly want to introduce some of the work that we'll be doing in the next year with our next roadmap before handing back to David. So we want to keep working on improving electrostatics, and this will take the form of 3 directions. We want to release our existing neural network project as an endorsed AM1 charge provider, and then after that, move on to fitting directly to higher level QM data, and we think that will improve our electrostatics quite a bit. We'll keep working on virtual sites, and if or when the current initial phase of virtual sites is successful, we plan to advance this by adding even more virtual sites, but also fitting them to a higher level of theory than HF612 star. And lastly, we'll start investigating polarizability, so largely building off Willer's very promising work here with direct polarizability. We want to extend the impact of our force fields, so not only will we continue working on the protein force field, but we're going to start looking beyond that and expanding our view into nucleic acids and lipids as well. And as a related goal, we want to extend the amount of coverage that we can handle from the PDV. So we'll start by measuring how much we can actually handle and then attempt to increase that fraction. We also want to extend the impact of our tools. So specifically, we want to continue developing and improving our benchmarking suite, as well as improving interchange and making interchange a widely adopted tool for system manipulation and combination. And finally, we're adding a focus on community growth this year. So we're very keen to build a self-perpetuating community around both our tools and our force fields. And we'll do that by further investigating in our workshop series, engaging with outside developers, and just encouraging the general growth of the force field ecosystem around us. So experimenting with alternative OpenFF format force fields, new features, and new functional forms. So that's a preview of what's to come. And I'll hand back over to David now.
Thank you. Okay, clicker. So just really quickly, I want to say why I think OpenFF is so important. One is that because it's open and flexible, you're not relying on us to fix all of the problems. In fact, if we're as successful as we want to be, we can close up shop and people will go on using our force fields and because it's so important to the community. So success means we get to go do something else. So that's a good model to invest in. Also, if we end up doing something that doesn't work out, our tools can still be used to do something else. It's community-based. I really love seeing the community come together to share problems, approaches, tools, scripts, work on solving our problems together. We have a shared interest in solving problems. And so you see that, for example, even in this recent benchmarking paper put together by mainly, it's an industry benchmarking paper. So you could see the authors list. If you look at affiliations, it's a bunch of different pharma companies, 10 or 12, which is great. Ultimately, we're in business to solve the problems we need to solve so we can use these tools to do the molecular design we want, we as a community. I'm working on force fields not because I wanted to, but because I kept having force field problems and there was nobody who would fix them for me. So for me, I'd love the force fields to be good enough that I can go back and focus on the other problems. And ultimately, most importantly, I think, aside from open force field, I'm not aware of any other open or public force field effort that has a sustainable model. So that's partly why I think this is so important. So in conclusion, we've released a new force field recently, improves things across the board, but especially for some specific problem chemistries. There's a lot more in the pipeline to come out soon, as soon as we can have it ready. I didn't show this graph, but we're making our systematic improvements in force fields actually have an impact in binding free energy calculations. The best significance tested benchmarks, which we could point you to, show clear improvements in binding free energies across force field versions for specific chemistries. But as people at the alchemistry meeting heard, often it's hard to see some of these changes because other aspects obscure the effect of force fields on binding, like protein prep, system prep, other issues like that. We're excited about Nagel and graph network models as an approach to charging that fixes a number of problems, but is also going to really facilitate the future, like easy handling of post-translational modifications and so on. Our protein force field is underway, and you could talk to Chapin more about it. We want to be able to deliver something to you that's better than the state of the art, so we hope that will be along soon. And we're excited about the stuff that people in the community are doing with our tools, ranging from polarization to alternate functional forms, all kinds of cool, Espeloma, other kinds of cool science coming along. So I think we probably have, want to acknowledge everybody who's been involved and supported Open Force Field. It's way too many people to list, and we also build on some of the great force field science that came before, even from Amber. We also really appreciate OMSF for support and Carmen for all that she's done to help this happen. So I think we have a couple of minutes for questions if anybody has any.